Apparently we're live. I wonder if my empty chair is, it's like time delayed. For the people who are watching the live stream, did it start with a video of my empty chair, or did it start with me sitting here? I would be interested to know what happens, whether it's like how far back the delay goes. Was it showing it before I pressed the button? So we were talking before the show. What a week. Like, I just want to apologize in advance to everybody watching and my co-hosts today that this show might either run long or we will not give enough effort to all of the stories as that they depend on it, because there was...
All the space news is happening this week, apparently. So.
Yeah, I'm calling it right now, and we're already halfway through. It's the most eventful week in space news for 2020.
It's a good thing, though.
Well, two good things, one
there's
really
been some
bad
sad
thing.
Things. Yeah,
maybe three good things, one bad thing. Yeah, we had one really bad thing, but then a bunch of...
I would say the Arecibo is a good thing.
Whoa, controversial take.
It's sad to see it like that. I mean, we knew they were going to decommission it now, but still, it's sad.
Well,
I saw the engineering report. It's a good thing that it went by itself with no one getting harmed. They were not saving it.
Yeah, it was. I mean,
so the fact that it went free and clear on its own without having to detonate it is a good thing.
Yeah.
Is that what they would have to do? They have to blow it up?
They'd have to explosively snap the cables.
Right.
Would have made an interesting video.
It would have made an interesting video, but it's more dangerous because people would have had to go into basically a danger zone to set it up.
The explosives,
Yeah, and you didn't want that. So this is actually the best scenario of all the bad ones that could have happened.
Yeah. And people...
I feel like you've successfully defended your hot take.
Yeah,
There you go.
People are, and we'll get into this, right? But people are asking, like, what are the chances of a rebuild? 0.
Pretty slim now.
What? Yeah. They kept trying to decommission it even when it was perfectly fully functioning.
Yeah, it underwent Hurricane Maria and an earthquake, and there've been multiple cable snaps this year. And...
Yeah, but there had been before this year. It was always on the chopping block.
Yes.
Yeah.
So, this is.
We're not going to get those pretty animations of passing asteroids anymore. That's what I always liked from Arecibo. Yeah. Well, Goldstone can do stuff like that too.
Yeah, and unfortunately, the FAST telescope, the Chinese one, can't support a radar instrument of that same capability. So, well, we're just doing the show right now. I guess that's what it's going to take for us to be able to fit all of the news in. Is we're going to do the show before we do the show, but. I'm going to I got to say hi to a bunch of people before we get rolling. So, hello to Six Bob Ohms, Alex Despland, Andrew Planet, Astro B, Ben Kalo, BTT, Cicely Douglas, Don Tovey, Frank Tippin, Greg Nickel, Harry Patrick, Ian Farquhar, John Seffield, Johnny J, Johnny Zed, Larry Beckham, Larry King, Luke Duke, Grenzi Graziano, Noel Ruppenthal, Arjone, Scott Bragdon, Susan Hunter, Tom Van Scotter, Trey Harmon, Visto Tootie, Zach Perry, and Zap Van Zap Van. Hey, everybody. John Seffield, you keep asking about the Great Attractor. If you're actually wanting to know about the Great Attractor, I'm happy to go into it. If you're just trying to troll me, well played, sir. That's just what I want to mention. So just tell me honestly. Just say if you want me to go into the Great Attractor, I will do it. But if you're just yanking my chain, on my show every week, people always ask me about the Great Attractor. I literally have to answer the question each week, and it's hilarious because it's not a mystery anymore. It's like literally it's a mystery. It's a 30-year-old mystery. In fact, we could make Brian do it. Okay, he really meant it. Okay, all right. Brian Coberlin, what is the Great Attractor in 1 minute?
It's a large mass of a galactic cluster that's in the direction of the center of the galaxy. So we can't see it directly, but we can see things moving towards it. But we've now been able to map some of it. We know what it is. It used to be that it was just like all of a sudden everything's being attracted towards something that we can't see. And now we kind of know what it is.
Yeah, it's just a bunch of galaxies. that happens
it's well done off the cuff.
There's nothing magical or special about it.
Yeah, so it happens to be a bunch of galaxies on the other side of the Milky Way. They had to be somewhere, and that's where they are. All right, so there you go. But now, from this point forward, John, you control me each week if you want. All right, I'm going to put you guys all back in your boxes. Back to me. Speaker view. All right. Here we go. Hello and welcome to the Weekly Space Hangout for Wednesday, December 2nd, 2020. I'm Fraser Cain, publisher of Universe Today. This week, we're going to be talking about the fact that we're now 2,000 light years closer to the center of the Milky Way. Chang'e 5 lands on the moon. Upcoming eclipse, meteor shower, the Jupiter-Saturn conjunction, big temperature changes in the universe revealed, the loss of the Arecibo Observatory, and more. Possible flight for Starship. It's going to be a crazy week, so buckle up. All right. Joining me this week on my screen, I got Dr. Brian Comerlin. Brian.
Hi, everybody. Good to see everyone.
We've got Moya McTeer. Hey, Moya.
Hey, Fraser. Good to be here.
And we've also got Dave Dickinson. Hey, Dave.
Hey, definitely not bored in 2020 yet, and it's December. So.
No. Your hair, my beard. I think we're both.
I probably got my last haircut this time last year.
Yeah.
And come March, I remember thinking I should get a haircut, and then of course 2020 happened. So like, nope.
Yeah, at some point we just keep rolling. We'll make it through 2021. All right, so before we get on to this week's guest, I just want to remind all of you that if you enjoy the show, you want to be a part of the show, behind the scenes, be an executive producer of the show, join the Weekly Space Hangout crew. Go to wshcrew.space. You'll get access to the behind the scenes Slack community, a way for you to be able to get your executive producer credentials so that you can then go and invite anyone on the show that you want. For example, our special guest this week, Ingrid Daubar. Ingrid, welcome to the Weekly Space Hangout.
Thank you for having me.
Dr. Daubar. Apologies. You got to put the doctor in your Zoom meeting.
I didn't go to evil scientist school for nothing.
Yeah, exactly. So, as I always like to ask people, who are you? What do you do?
So I am Ingrid Daubar. I'm an assistant professor of research at Brown University. And I study craters mostly, especially really small craters like this one, which is going away. This one.
Yeah, you chose a very nice crater.
Yes, this is a very beautiful one that just occurred on Mars within the last couple of years. And the reason I get excited about these craters in particular are that they're really new. They're constrained to have happened within the last couple months, couple years. So they're currently happening on Mars, which I think is really exciting. And we're able to use orbital imagers to find them. And we have a database of about 11 of 100 of them right now. So, and we're finding more every day.
Why do craters matter?
Why do craters matter?
Yeah.
So craters matter for a number of reasons. I mean, first of all, it's a process that's occurring throughout the solar system on every solid surface. So other than maybe Io, I think, right? Every solid surface has craters on it. And so we can use them to both investigate the physical processes of cratering, to look at what's hitting all these bodies, right? Like what are the impacting populations? Are they sourced from comets or asteroids? We can use them to probe the subsurface. So on Mars, some of these new craters actually revealed shallow subsurface ice at the mid-latitudes, as low as like 40 degrees latitude, which is pretty cool for future in situ resource utilization, for example. And we also can use older craters to just date surfaces. So the ones that are this small, we already know how old they are, but on older surfaces, we can use the spatial density of craters of different sizes to get an idea of how old that surface is. And that gives us an idea of the whole history, the geologic history of that body, what's happened on it and when, and how that relates to the whole history of the solar system.
And you were part of a team that used artificial intelligence to count craters quickly and efficiently.
Yeah, they didn't actually count craters, although I think other people are trying to do that. I don't
classify.
know if that's, yeah. So what they did was they had a machine learning algorithm, and they used a classifier and they trained it on my database of fresh new craters on Mars. And because these are found in lower resolution data, this is a really high resolution image, but they're found in lower resolution data. So they really just look like little dark spots, but they have a very distinctive appearance. So this was a problem that was really well suited to a machine learning application. And we have 1,100 of them, so they had lots of training available. And so far they've been able to find quite a few that we didn't know about, actually.
Sorry, 1,100 fresh craters?
Yeah, we know of about 1,100 where we have before and after images, and we can track how old they are. Yeah.
On Mars or on the moon as well?
On Mars,
okay.
Primarily, but this kind of study we've also been doing on the moon, and they're finding similar densities of craters. It's a little bit different there. It's a little bit harder to find them, and the data sets are different. And there's a lot of just kind of splotches on the moon where we can't see the actual crater, but there's it's kind of overturned the surface, so you see brighter stuff underneath.
And so I can really imagine that you're like really looking for a needle in a haystack. You've got some spacecraft like the Mars Reconnaissance Orbiter that's going around and around Mars capturing images of it, but it's not going to catch the craters in action. And so how do you know which are the new craters? So what is the value of a brand new crater?
Yeah, so just to address your first point, yes, these are tiny. There's no scale bar here, but these are just meters in diameter. So finding them over the entire globe is really hard. Part of what allows us to do that is this really big dark blast zone around it. So in lower resolution data, we see this dark tiny dot, but when we zoom in with HiRISE, we actually see these tiny craters. And then your second question was about the value.
Well, what's the value, of a brand new crater?
Yeah. So a couple things. First of all, we've been able to calibrate our chronology systems. So when we look at older craters to estimate the age of a surface, all of those models are based on lunar craters that are really old, and then kind of extrapolated out to Mars in the current day. But we've actually been able to calculate how many things are hitting Mars of a certain size per time. And then we also get the really fresh craters. I mean, other than in a laboratory, we don't see craters this fresh anywhere else in the solar system. So we're able to look at the shape of really fresh craters and what's underneath the shallow subsurface there. That ice, for example, sublimates away pretty quickly. So we really need the fresh craters to find the ice.
That's interesting. So it's kind of like a supernova, that you see one of these, you catch a new one, and then you're able to see the volatiles, see some of the stuff that maybe will disappear as the season changes. Do you think being able to catch these even faster will give you more science? Like if you could know about a fresh crater within a day, would that tell you more than knowing it within the year?
That's a really interesting question. For the icy ones, I think it would. Because that ice does go away fairly quickly. It sticks around for long enough that we know it's really pure ice. It's not mixed with a lot of dirt or dust, but that still means, months to years. And so we're definitely missing some of these, right? Because we need two images. We need a before and an after, and they have to be pretty close in time to even be interesting. And it happened, and that crater has to happen in between them, and we can't plan that.
Yeah.
So yeah, certainly, we've played around with concepts like, what if we had just like so much data volume and so many images, orders of magnitude more images than we have now. What would we do with that? And finding new craters faster is definitely one of the things I would love to see.
I got an interesting question from Vista Tutti in the chat. Any fresh craters near a Mars rover? Like, is that the dream, having having new craters so close that a rover could just?
So, I'm on the InSight team, which is a Mars lander that has a seismometer, and we initially thought that impacts would be a really useful source of seismic signals because they provide a known location for a seismic source, right? So like a Mars quake, you don't really know exactly where that happened, and the localization has really big errors on it. It could be in a really big error ellipse. But an impact that we have an image of, we know exactly where it happened, and we know pretty much when it happened from the seismic data. So that is the dream. Mm-hmm. However, so far we have not detected an impact seismically. However, one did occur right near the rover. It was only about 40 kilometers away from InSight. And it happened right after we landed, and it was really, really exciting, but it turns out it was so tiny that it didn't even make a detectable signal. So we're still hoping though.
Could you go the other way though? Could you detect, say, an impact from InSight and then be able to reverse engineer where it happened?
Yeah, initially, actually, that was going to be our approach. We were going to pick out of the seismic signals which ones were impacts. We have a number of different ways we thought we could tell impacts from quakes. And then we were going to go and with the Mars Reconnaissance Orbiter, try to image that location. Unfortunately, all of the different discriminators that we came up with to differentiate impacts from quakes are just, turns out, really hard to do on Mars. There's a lot of scattering in the shallow crust, and that really masks a lot of the different aspects of the seismic signal that would have helped us out with that.
So, I mean, at this point, scientists know the history of the solar system, like, you know, with the late heavy bombardment and some of the other phases. Does being able to get access to this many new craters and maybe even being able to start classifying more craters, does it allow you to fine tune the history of the solar system at all?
Well, it's a process that's happening right now. So it's hard to extrapolate that back too far. But certainly the physical processes that are happening have always happened, right? So bits and pieces of things have been hitting Mars for 4 billion years, and they're going to keep doing that. You know, I don't think there's too much we can do to take the current rate and extrapolate all the way back, but we can certainly connect it with the bigger picture. It's one small piece of the big picture.
So, you know, in the hope is that we're going to be having humans going back to the moon in the next couple of years, that hopefully we'll eventually have humans going to Mars and some kind of permanent science station there. If you could have astronauts, geologically minded astronauts with their hands and clever minds and scientific equipment, what questions would you love to be able to have answered for you?
About these craters or about
craters and about what caused them? I mean, I was sort of thinking about this, like here on Earth, because we've got such a thick atmosphere. When the meteorites strike the atmosphere and they make their way through, they land, you know, out in Antarctica, just like you just pick them up. But I'm assuming they vaporize on Mars. Like you can't go out and collect samples from.
Yeah, so it's true. There is a thin atmosphere, which is like just enough of an atmosphere to cause problems, but not enough to really block these impacts. But one thing it does do is it fragments a lot of them. So about half of these are actually clusters with a bunch of craters in them. So we've been studying, you know, the way that they fragment in the atmosphere.
Ingrid,
go ahead.
Oh, haven't they found some? It seems I remember they picked up some actual meteorites on Mars, like Spirit and Curiosity, I believe.
Yeah. So the rovers have encountered things that are almost certainly meteorites. They're like chunks of iron. It's really hard to imagine what else they could be. And that is just such a mystery to me. I don't think that's really solved because how do you survive an impact at those high velocities? It was either coming in really slowly, or maybe the atmosphere was thicker and enough to slow them down enough so it just like gently landed.
You started with a much bigger object.
Yeah. But then it would have been a pretty big impact, right? It wouldn't have gotten slowed down as much if it was started out really big. So yeah, it's kind of I think that's a really interesting problem. But when we send astronauts, we should definitely have them look at those meteorites.
Yeah. But if it
there might also be some chunks of the Earth, which would be really cool.
Well, and I guess that's what I was hoping, which is that if here these meteorites are pretty tough to find, you know, they have to go out and drive around. But on Mars, for example, if they do leave some kind of debris behind, even if it's just vapor and powder, you could get some kind of insight, like, oh, that was Vesta. Oh, that was a little piece of a Jupiter Trojan or whatever. That each one of these is a little science experiment for you to go in and cover.
Yeah, certainly if we could go to it right after it formed, before all of this had eroded away, it'd be really interesting to see like what's all this blue stuff, right?
Yeah.
And I'm really interested in the dust. So there's a lot of dust around here that's been cleared away, and I'd like to know more about that.
It was interesting. There was a paper that I was looking at on Archive just a couple of days ago that someone was saying that you could use the moon as essentially a historical record, like tree rings for the entire history of the solar system, even just like the local astrophysics. Like you could find all of the supernova nearby, all of the times that Earth was hit by a gamma ray burst, et cetera, because it's, all of that is just layered in the top surface of the moon and Mars. I mean, Mars is tougher because it's got wind.
There's been some erosion there, right?
Yeah,
but the moon is much more stable.
Yeah, so it feels like you're reading the history book of the solar system. So what are you working on next? What is sort of what's your big plan now that you've got a way to find new craters? What comes next?
Yeah. So this is kind of just the beginning. So that news story that you picked up was about just the first one that we found and were able to confirm with the high-res camera. So we hope to do that with a lot more. And I think one of the big questions, at least in my mind, is, are these craters that we're finding with machine learning different than the ones that we found before with humans? And are they forming in different regions? Are they smaller? Are they, different contrast with the background? And what does that mean for potential biases in our data set?
I was just wondering,
are we really missing a lot of
we definitely see bias in artificial intelligence in general, and it would be interesting to see where that bias reveals itself in the way human beings even perceive craters and say, okay, these are craters, those aren't craters, and then the computer disagrees with us, and then suddenly, wow, maybe we don't recognize craters the way we thought we did. That's really interesting. Well, so if people want to find out more about what you're doing, where should they go?
Well, that's a good question. You can go to the HiRise website to see a lot of beautiful pictures of these craters, which is uahirise.org. And I would say stay tuned for when we get more of these than just one.
Yeah. Terrific. Well, thank you so much for taking the time to chat with us today, and keep us posted.
Great. Thanks a lot.
All right. Take care.
Bye-bye.
All right, let's move on to the news portion of the week. And like I said, buckle up. It's going to be a busy show. But before we get into the news that any of my co-hosts proposed, we've definitely got to talk about the elephant in the room, which is the complete and total collapse of the Arecibo Observatory. Brian Coberline, you had a hot take before we even got started on the show. Why don't you tell us how you think about this?
My point was the collapse was actually a good thing. And
it was a stupid observatory. Who needs it? Yeah. Here ends the show.
Yeah. But you might remember that it was damaged earlier. And after that initial damage, there was some engineering reports. And if you read through some of them, they are scary. This was in a dangerous situation. And when they said that they were going to have to tear it down, that meant putting people in harm's way to be able to set it up for a controlled collapse. And the fact that this is now collapsed on its own is actually the best of worst outcomes, because it means that it's collapsed. No one was injured. It happened overnight when no one was at risk. And so now it's much safer to be around. It can be dismantled in a safe way. And we don't have to put people at risk to do the sad task of disassembling a telescope, because the whole area has to be returned to its original condition. So that's part of the deal, is that when you pull a telescope out, you have to restore.
Right. And this is not the first time that a science facility like this has been shut down, although this observatory is a one of a kind.
It's iconic. I mean, it's been in movies more than one, and it's what people think of when they think of radio astronomy. They think of Arecibo.
Yeah.
I was saying, having the planetary radar to ping near Earth or asteroids, it really had a unique capability there to give us those kind of insights.
Right.
And I know a lot of people want to know, when are they going to build a new one? Brian, when are they going to build a replacement Arecibo, like right where it was? Fresh?
Right now, there are no plans to replace it. I mean, it's just too early to tell. There are radio telescopes in the works. I would hope, and I'm not privy to anything, but I would hope that Puerto Rico would get some type of radio facility. It's a good location. It's good to have a radio observatory there. What that might be is hard to tell. Part of the thing is that radio astronomy has changed a lot. And so the reason that one was originally built was because the bigger the telescope, the more precision and stuff you get better resolution. Well, now most of the radio telescopes we have are arrays. So there are arrays of antennas that work together to create a virtual antenna. Mm-hmm. So in some sense, Arecibo, although it had some very specific things that it could do, is kind of outdated in terms of the way we typically do radio astronomy.
Except for that radar ability, which is partly covered by Goldstone, but still.
Yeah.
Right. And also Green Bank is getting a transmitter.
Right.
Yeah.
And you can't put that kind of a radar instrument on the fast telescope, the Chinese one, the 500. So it can cover the rest of the science.
There were clearly things that only Arecibo could do. You know, everything from doing the radio pingings of asteroids to actually sending a message to the stars, which is, was also known for doing. And we don't have the ability to do that with other radio telescopes.
Yep. So unfortunately, for now, the news is terrible. Arecibo is gone, and there will be no replacement. So,
I did hear that all of the Arecibo Observatory cats were okay, though.
That's great. Yeah,
yes.
That's important. And I guess they're going to need to find new homes. All right. Dave Dickinson, let's talk about Chang'e 5.
Yes, last week, China launched one of its most ambitious moon missions, Chang'e 5. And this is leading up to an actual sample return. It's really a whirlwind mission because it launched from Wenchang Space Center last week on a Long March heavy rocket. And it went into orbit this past weekend. It landed yesterday and near the volcanic feature, the Mars Rumker feature in the Oceanus Procellarum region of the moon. It landed near it. It didn't land on it. I think that was for safety concerns, but they wanted to definitely land where the ejecta blanket is. Yeah, the video is kind of interesting when they're coming in because you see the camera when it pivots. It's very almost like an Apollo landing when they go in, and they really did a pinpoint landing. China's getting really good at this actually with these because they did a far side landing with Chang'e 4 last year. They did a Chang'e 5 T1 mission to kind of do a proof of concept for orbiting the moon and bringing the sample return back in 2014 because they're doing an interesting kind of skip reentry landing on Inner Mongolia. Yeah, that was one of the first pictures we got of the surface right there yesterday. And it's interesting because these are all trickling out. China, their space program is kind of an enigma to the West. They don't do a lot of press releases. They don't do a lot of interviews. It's hard for us to get any kind of quotes from anybody.
Yep.
We're mostly monitoring their state-run television for these high-profile missions, sometimes which they broadcast on CGTV, on the China state-run television, which streams on YouTube. And it's interesting, there's an interesting aspect of amateur radio astronomers were following this on ham radio, literally. They were following the mission, guys like Scott Tilley over in the UK.
Yep.
And we were following, this was all kind of leaking out on Twitter where they were getting the signal and they were saying, okay, it's in orbit now. And then now it's descended to this periapsis around the moon and things. So it's interesting how the information is kind of getting out almost like it kind of did during the Cold War, where we would hear, okay, the Soviets launched something and landed on the moon last week, where it only kind of trickled out later on. But we've got these images and they're actually going to they did the sample acquisition last night. This is interesting. They landed yesterday. They did the sample acquisition really overnight. Mm-hmm. They're taking off the ascent vehicle. If we can understand what we're seeing from their mission control, like over their shoulder, what we're seeing on the boards, they're probably the launch ascent vehicle is launching tomorrow morning to bring the samples back. So that's like, when you consider missions like OSIRIS-REx, that's taken years to get its sample back. It's coming back in 2023, or Hayabusa 2 coming back this weekend. That took several years. Of course, the moon is much closer and easier to get to, but they're going to probably be back around the 15th or 16th of this month. So that's going to be really quick.
It is really amazing that they're going to get the sample back pretty much within 3 weeks of the launch.
Yes.
And from a region of the moon that's really never been sampled before.
This This is very young. Like I said, there's not a lot of, in Mons Rumker, you can kind of see it with a medium-sized telescope. I was imaging it this weekend, kind of leading up to this landing, just for gee whiz. But you can see it's a volcanic feature, unlike a lot of the craters you see. So they're thinking that the material they're bringing back is only 1.2, 1.3 billion years old, which for some context, most of what the NASA astronauts what they picked up in the Soviet automated missions picked up is more in the regime of 3 to 4 billion years old. So this is going to be a very young lunar basalt kind of sample. And they're bringing back actual cores. These are going down about 2 meters.
That's right. Yeah. So, I'm trying to find some animations that I can actually play.
There was an interesting one. Andrew Jones, I think, posted. There was an animation where you could see it doing the drilling action and stuff. So
yeah, the person that I recommend is definitely Andrew Jones. If there's one person who has their finger on the pulse of what's happening with China,
primarily on the Chinese space flight aspect of what they're doing. But yeah, so it's going to be interesting that they're going to be. There's an orbiting service module that they left up. It's very Apollo like how they're doing this actually, with a lander, an ascent vehicle, a service module. Yes. So it's going to be taking off tomorrow. I wonder, we might see some images of the ascent vehicle taking off. That would be kind of interesting.
It can't. I mean, come on. Right? Like, you're sending a spacecraft to the moon, it's landing gently on the moon, it's taking a sample, and then the ascent vehicle is launching from the surface of the moon and returning safely back to Earth with a capsule. Like, that's just on the roadmap for sending humans. They're also have building space stations. Like this
China's
is where it's all going.
China's kind of getting into new territory for them. Once they've never launched from the surface of the moon. They've never done the lunar orbit rendezvous in the return. Well, they've done the return. Like I said, they did Chang'e 5 T1 a few years ago just to test this skip reentry over Inner Mongolia. And they've really been doing this in stages, like practicing the landings first, practicing the reentries first, so everything has got to work as automated, but I'm impressed how the landings, you think about, we had a string of failures. India's lander failed last year. Israel's lander failed last year. China really has done pretty well. Their landings haven't failed. They've sticked all the landings on the moon thus far.
Yeah, and I think like right now, I think they've got 3 operational landers on the moon.
Yeah, it's interesting. We still hear from the one in Sinus Iridium, Chang'e 3, ham operators. And this one, too, is solar powered. That was the other thing. They landed right at sunset or sunrise at that area. You have about 2 weeks of daytime on the moon until the sun sets again. So they really had to kind of get going really quickly. This one has no nuclear RTG. It's just solar powered. So once the sun sets on it, it's done.
Yeah.
So,
yeah.
But
yeah,
it'll be interesting to see. Well, like I said, we have how often. Well, we've never had 2 sample returns come back in a weekend because Hayabusa 2 is coming back from Ryugu with its asteroid sample return on December 5th, this Saturday. So it's coming back. Well, not of course Chang'e 5. The sample return's not coming back this weekend, but it's coming back in mid-December.
Yeah.
So
yeah. Yeah, absolutely fantastic. I'm super excited to see. I hope they share the sample. I know NASA tweeted. It
was interesting. NASA tweeted that kind of started a minor controversy online too. That people were and that, of course, the SLS. There are some moon missions going up next year if SLS goes next year. Next year, SLS and James Webb may go. So that will be interesting. That's an uncrewed, the first SLS flight, but. Yeah. There are some small sats on that are going to the moon on that one.
Yep.
So
awesome. Thanks, David. All right, Moya, let's talk about the history of the temperature changes in the universe revealed.
Cool. I feel like you're trying to avoid saying the name.
I'm not going to say it. Sunyaev Zeldovic.
Right. So this article is about the Sunyaev-Zeldovich effect, which I'm going to say as many times as I can. So if you zoom like way, way, way out into the universe and you look at the universe as a whole, you'll see that all of the matter exists in this vast network of material that astronomers call the cosmic web. Yeah, looks like that. It's beautiful. But a lot of that matter is gas. And as it gets drawn into the cosmic web by gravity, it smashes into each other and the gas heats up. And this means that the gas in the universe is really hot because it's been heating up over a very long time. And astronomers at the Kavli Institute just figured out how hot it is after studying it for 20 years. It took that long. So when photons from the cosmic microwave background pass through this hot gas in the universe, they can get scattered by electrons in the cloud, which makes that gas visible in a way that it wasn't before. And this is called the Sunyaev-Zeldovich effect, named after two scientists who worked separately on the problem.
So the effect is using for the measurement, not the actual heating up of the gas.
The effect is the photons getting scattered by the electrons in the gas cloud.
Right. And that's the way that you can then use that to measure the temperature of these regions.
Exactly. Right. Yeah, because the brighter the signal is, the hotter the gas is. Because it's related to the thermal pressure. As things heat up, they start moving faster. So the reason it took so long, it took them 20 years, is they used 15 years worth of data from SDSS and the Planck satellite, and they had to have a specially made physical model to calculate the average temperature. And then they spent 4 years analyzing the data. So it took a long time. And they found that the gas has heated up over the Hubble time, over the last 14 billion years, which makes a lot of sense because more time just means that there are more opportunities for the gas to smash into each other and get heated up. So 8 billion years ago, the average gas temperature was about 700,000 Kelvin, and now it's closer to 2 million Kelvin, which is a lot hotter than the average temperature of the universe that gets thrown around, which is 3 Kelvin.
Right. And of course, this is specifically because you're seeing this concentration of all of these giant galaxies coming together, and they're heating up and heating up and heating up as they get closer and closer together.
Exactly. Yeah.
Yeah. Very cool. I love like how long it must have taken them to like write this paper. Like you said, like more than a decade of gathering this data, and they're like, finally submit to the journal.
Yeah, I'm impressed. I haven't done anything for 20 years, so good for them.
Yeah, absolutely. All right, Brian.
Yes.
I choose. Did you pick two? No, let's talk about being closer to the center of the galaxy.
So obviously the sun orbits within the Milky Way at a distance from the supermassive black hole in the center of our galaxy. And the official distance in terms of the International Astronomical Union is 27,700 light years from the black hole in the center of our galaxy. That's the official distance. Right. And finding that distance is actually really difficult because we're in the middle of the Milky Way. And so our planet is orbiting a star that's in the middle of this. You can't see everything. And you don't have any fixed reference point. So you have to measure where all the other stars in your neighborhood are and how fast they're moving and in what direction they're moving. And you do a whole bunch of math and try and figure out, okay, that means we're this far away from the center of the galaxy. So they've done this, and the official value comes from 1985, when it was all done with optical telescopes. So recently, there was a project, Vera, which is the very long VBLI, what was it? VBLI something. I can't think of it.
It's one of those annoying nested acronyms.
Yeah. Sorry, VLBI, Exploration of Radio Astrometry. So I'll just call it Vera. It's my very favorite term. So this is actually an array of radio antennas in the archipelago of Japan. And VLBI stands for Very Long Baseline Interferometry. And basically what it means is instead of creating a really big radio telescope, you're doing a whole bunch of antennas that are scattered apart. And because light takes time to reach them, they reach some antennas before they reach other antennas. And so you can correlate the data using interferometry in order to basically act as a single virtual telescope.
Right.
So this Vera array has a baseline of a diameter, effectively, of about 2,000 kilometers. And so it can act as kind of a virtual radio telescope 2,000 kilometers wide. This means that when you look at specific stars, you can pinpoint more precisely where they are, as well as how they're moving. So they used this array, they looked at 99 stars, and they found their positions to within 10 micro arc seconds, which is about the same as taking a penny and placing it on the moon. And you can find the penny, that's where it is. So using this data from the stars, they could actually do a more accurate measurement of our distance from the center of the galaxy. And what they got was 25,800 light years. So about 2,000 light years closer.
So, okay, so I want to see if I understand the method here, just so we're really clear about this. Like, because we're orbiting around the galactic center, the distance of the galactic center isn't changing. So we can't measure like the Doppler speed of the galactic center as we're moving.
Right. The sun is basically in a circular orbit.
Right. The galactic center is not a Cepheid variable, so we can't use that technique to determine the distance to it.
Right.
And even with astrometry, I guess we could, but astrometry taps out at a certain distance. Like, you can't go that far with astrometry, right?
I was to say, like, Gaia doesn't even do down like in the micro arc second. That's really
yeah. But astrometry, you get to a certain point, you can't do astrometry anymore because it's just moving. I mean, even the 5 micro arc sections. So they looked at all kinds of different stars all around, or did they only look at stars in the middle of the galaxy?
So they looked at, if you think of, here's the Milky Way, here's the sun. They're looking at stars kind of in that side of the Milky Way that we're on.
So they looked away
how close we are and outwards.
So they looked away from the center of the Milky Way.
They also looked towards the center of the Milky Way.
Right. And so the trick was by figuring out the distance to all of these stars that were around them, they were able to sort of calculate what layer we're on going around the center of the Milky Way. Is that right?
So they find out where these stars are. They find out where they move from our point of view, what would be the kind of transverse one. Then they can use the Doppler effect to determine the radial motion. So they not only know where the star is, they know how fast and in what direction in 3 dimensions it's moving.
So it would be like you're on a racetrack, you're on Daytona or whatever. You're watching a car pass you on the outside, and that tells you how far away you are from the center of the track.
Basically, yeah. Because if you map out all the orbits, you then know basically what they are all orbiting. So basically, you assume this a Kepler orbit is what you're assuming.
Yeah.
And you have this little orbit. And if you know that orbit has a center here and another star has a center about here, and then all of those calculated orbits have centers, and you do the statistical sampling of it and go, okay, so that means the best measurement we have is this. It's 25,800 light years away.
Wow. That is incredible. What a phenomenal feat. And the result is we are 2,000 light years closer to the center of the galaxy than we thought.
Right.
So we're not as far, in the outer neighborhoods. We're actually kind of close to the bustling city center of the galaxy.
Yeah, we're in the bustling suburbs, basically.
Bustling suburbs.
That's another thing in my books that is obsolete again now. So.
Yeah, great. Yeah. Now I gotta come up with. I gotta change my notes. I got so many articles that I'm gonna have to go and redo.
If there's ever a second edition.
Yeah.
Yep.
Yeah.
Speaking of astrometry, Gaia's early 3rd data release is coming out tomorrow morning.
Yeah, I saw that.
Very excited.
Yeah. I mentioned that on Twitter, but yeah, we are only now about 8 hours away from Gaia 3.0. Yeah.
Very.
Which is what, 1.4 billion star measurements, I think, is what they're talking about.
Yeah, it's about
Yeah.
1.4 billion with slightly better parallaxes and proper motions, about 20% better parallaxes, better proper motions by a factor of 2, but no new RVs. Those are going to come out in the full third data release.
But will this one have the planets?
I don't think so.
Because they're
Yeah,
anticipating finding about 50,000 planets through astrometry.
I have heard that. Yeah.
Yeah, and I
don't-
thought it
don't
was
know if
coming
that's
with
gonna be
data
out of
release
this one.
3. So, but I could be super wrong. I might be wait for the full one. But yeah, like
Probably after data release 3, people are going to start mining it.
yeah, but it's just like as a side effect of this incredibly precise map of the
Yeah.
galaxy. Oh, by the way, we've also found 10 times more planets than anybody's ever found ever.
Gaia's
Especially
another-
ones that are facing us.
Yeah.
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 Gaia's another amazing mission most
Yeah.
people have never heard of. That's done some amazing
Yeah.
stuff.
Yeah, I'm so excited by astrometry. I don't know what's wrong with me, but I just love astrometry so much.
There's nothing wrong with you,
Okay,
Fraser.
all right.
I am biased.
Okay.
You always want to know where you are.
Yeah.
Well, yeah, this stuff
Yeah.
has changed since even you're about the same age as me, Fraser. So it's like this stuff, when you look back at textbooks from the 70s and 80s, this stuff has changed a huge amount as far as how far like the Pleiades are. And it's amazing.
I love
that-
these general tools that are just available to use for all kinds of ideas. Like if you just come up with that idea and someone goes like, hey, I bet we could find white dwarfs in binary companions. Oh yeah, just look through the Gaia release. There it is. There they are.
And
Yeah.
I learned when I was writing this book, like doing all the distances to open clusters, that we don't know these as well as we really think. That's one takeaway I had from the research is some of these open clusters, like even in the Messier catalog, we don't have the distances pegged down as much as we think we do.
The fact that we thought that Betelgeuse was 640 light years
Yeah.
away, and now it turns out it's 25% closer and not going to explode as soon as we thought. You know, we were all just like parroting 640 light years, 640, and someone,
Yeah, I
I'm
know.
sure, said, "Are you sure?"
Well, it's only
Check
100
Gaia.
years ago that we even knew that we're not in the center of the Milky Way.
True, yeah.
It's only 100 years. It's only a century that we've been able to map out that we're
Yeah.
offset from the main portion of the Milky Way. So this is still young science.
Yeah. Larry Beckham is saying in the chat, Gaia, the finder scope for LUVOIR. I think that's exactly it. I can't wait to see people turning observatories on all of the interesting stuff that pops out of Gaia. And then there's even some on archives, some proposals for like next generation Gaia. Well, like, how could you juice up Gaia to have an even better astrometry mission? Maybe you could do something at that same, like what that Japanese team did with Vera, but with a larger catalog of stars. So, all right. Give us your next story.
All right. I just got a kick out of this. So in 2005, 2 theoretical physicists wrote a paper that said, well, if there is an intelligent creator of the universe, they might have left us a message. And if they did, it would probably be found in the CMB because it's literally the oldest signal we have. So yesterday, building off of that, a researcher named Michael Hipka put a paper on the archive where he tried to see if there was, in fact, a message in the CMB.
How did I miss this?
Oh,
my
it's
God.
amazing.
We are totally stealing this for Universe Today. Just warning you,
Good.
this is gonna go up on the site. Yeah. So okay, all right.
Awesome. Yeah, so he looked at the temperature variations in the cosmic microwave background, translated that to a binary code with, like 1,000 bits in it, and then ran that through a bunch of tests to see, is it random? He compared it to some of the more common mathematical constants that we see everywhere in nature, like pi and e. He didn't see any of those patterns. He ran it through this battery of statistical tests that people use to see how good a random number generator is. And it turns out that the code is very random. So there's no message, or at least no meaningful message that we can interpret in the cosmic microwave background.
If you're using binary,
right? Yeah, and so that there are a lot of assumptions that go into that, but
I mean, you always hear people who like analyze like biblical texts and things like that, and they find whatever they want in that through just looking for enough. They see, oh, we found E and pi and whatever, just depending on how you massage the data. And so I wonder, just by making this data available, other people are now going to be able to grind through it and see what they can find.
Yeah, it's really interesting. The way that he translated it into a binary code seems to be comparing the variations to models, and then based on the residuals, like if it's above a certain threshold, it's a 0. If it's below, it's a 1 or something like that. It's an interesting process.
Yeah,
it sounds like the book version of Contact at the very end, where I think it was either in the Planck constant or pi. They found some sort of pattern or something that was like embedded in it. Yeah.
Mm-hmm.
Yeah, it wasn't in the movie, but the book version.
In the book, yeah. And I've heard about someone else proposing something similar to this, and I wish like using it for encryption or something like that. Oh, I forget what the research was, but the point being, no proof of a creator in the cosmic microwave background radiation so far.
Right.
Okay.
So far.
Keep looking. All right, Dave, we've got a crazy month coming up of cool space astronomy, amateur astronomy.
Yeah, 2020 kind of saved the best for last as far as observational astronomy. We had a penumbral eclipse, of course. We were clouded out here Sunday, but that started, I saw some images that some people did get a little bit of the shading on the moon. Again, not really an amazing eclipse. But in 2 weeks, it leads up to a total solar eclipse. Of course, we won't see it here. That passes over South America.
Yep.
So, and right now with all the pandemic restrictions, all the eclipse chasers have their wings clipped. So there's a lot of sad eclipse chasers that can't go to South America right now to see this one.
Yeah, I wonder, like all the hotels are going to close. Like there's going to be just a few lucky people that happen to live under the eclipse path.
This one really passes over remote area Chile and Argentina too. So
yeah, I think a quick right across.
Yeah, some locals will see it, and it will be partial all the way across South America. They will see it there. But what's interesting with the moon being new that same day on the 14th is one of the best meteor showers of the year, and that's the best moon phase you can have is the Geminids peak on the right around that week as well. And the Geminids in the last few years have been really better than the Perseids, really about 200 per hour. So that's always a good draw and a good dependable meteor shower. So that's going to be a big deal. And then, of course, we have the conjunction right on the winter solstice of Saturn and Jupiter. Not really anything scientific going on with this, but it's going to be a cool public outreach thing because Saturn and Jupiter will be, for the first time that we've ever had in our lifetimes, 6 arc minutes apart. So you'll literally be able to put both gas giants in the same eyepiece field of view. Mm-hmm. So it'll be a neat thing to show. I ran a simulation looking to see just how rare this was. I mean, this is what I do for fun.
Yeah.
A computer searching through 20,000 years of conjunctions of Jupiter and Saturn, and I only found 58 that were closer than 10 arc minutes. Now, when you're looking at predictions like 10,000 years in the future, they get a little less certain when you're, the 3-body problem and things. But when you're looking at 2,000 years of observations, like from say 1000 AD out to 3000 AD, those predictions are pretty good. And there's only 11 times that Jupiter and Saturn have a conjunction closer than 10 arc minutes. That's about a third the size of the full moon. And there are only 5 that are closer than this 6 arc minute one. So this literally will be the closest one. The last one in our lifetime was in 1623. And the next one, or not in our lifetime, but the last one that happened, period, was 1623. And the next one, some people might live to see. There's one nearly as close in 2080 that Jupiter and Saturn will be that close. So it's going to be a nifty thing.
That'll be you. Let us know how it works out for you.
Yeah, unless they they do the Futurama, put our heads in jars.
Yeah,
thing,
you take our heads in jars out to the site, and we'll see it again.
That's a promise.
Were you able to find any like closer, like ridiculously closer, going back or forwards in time?
There was, I think it's out in the 8000s. Jupiter may actually occult Saturn. Again, these get a little less certain when you're looking way out in the future, but when an occultation is when the object actually passes in front. So Jupiter actually, that would be weird to see because Jupiter would have rings, actually, because Saturn would be behind Jupiter.
Oh.
So if you're looking over absurdly long lengths of time, these sorts of things happen where you'll get a planet passing in front. The moon occults things every month, you see. Somewhere in the world, it's either passing in front of planets or stars, but it's a large body. To see something like a planet pass in front of another planet is, I think there's one out in 2060 that I think Venus occults Jupiter that we might live to see. We'll be in our 90s by then. I'll be in my 90s anyway. But so that would be, there are some really, if you look out, like some really crazy things, like to see Venus and Mercury transit the sun at the same time. I think somebody had looked that somewhere around 60,000 AD, we might see something that improbable. I know back in the 90s, we had the moon occult. I think it was Venus and Jupiter at the same time. That was really, really rare. That was for like the Southern Atlantic. So I didn't actually see it, but you know, some of these really, and I think I'm going to make a prediction that, you know how we always do this, what was the Star of Bethlehem story comes around every Christmas.
Yep.
Probably it's going to make its cycle around with this conjunction happening right before Christmas. We're all going to be dusting off our what was the Star of Bethlehem stories again.
2012 on the 21st of December?
Yes, there was a big to-do about the fact that it was, so
maybe this is the apocalypse year.
Well, it is 2020, so who knows?
It's sure try.
Rumor about that they were off by 8 years.
Yeah, exactly. All right. Before we go, one last piece of information, which is probably Friday. SpaceX is targeting their next launch of the Starship. They are going to do a static fire, one final static fire of the rocket, and then they're going to try to do that 15-kilometer hop.
15-kilometer hop.
Yeah, by the end of the week. So if all goes well, I mean, the one that they've got with the little flappy flaps will blast off. It's got 3 Raptor engines on board. They had a failure of one of them about 2 weeks ago, and so they had to go and rebuild that, and that pushed back the launch. But they've got road closures up for the next couple of days, and so this could very well be the moment when we watch that grain silo fly out of sight.
I think it's neat that, like we're talking about watching the Chinese space program, that there are people that do nothing but watch Boca Chica just to see what's going on.
Yeah. And of course, I mean, this isn't orbital, but this is, you know, at this point, SpaceX will be capable of doing what Blue Origin's New Shepard can do, which is fly up to, well, you know, New Shepard will go up to 100 kilometers. This will only go to 15 kilometers. So, you know, you got to catch up with Jeff Bezos and team, but nice try, Elon Musk. Elon Musk has also said that the plans are still to send humans to Mars by 2026. And in fact, if you go back to 2016, he said, I'm going to be sending humans to Mars by 2026, 10 years. And even a couple of years ago, he continued on that. So just a couple of days ago, he said they're still on track to send humans to Mars on Starship 2026, maybe 2024 if they get lucky. But definitely things will be going to the moon by 2022.
They may be sending tourists up on Crew Dragon next year.
Yeah.
Some of the manifests, there is one tourist flight next year on Crew Dragon.
But of course, even if this thing does fly, it's that getting back through the Earth's atmosphere part that's going to be the tricky part that could stall the development. So, but still, I cannot wait. I will be watching live when they decide to fly this grain silo, and each step moving forward to fully reusable rocket flight is really exciting. So good luck to everybody at SpaceX for a safe and successful flight. All right, did we cover everybody's news? I think we did, and we kept the time well, so I think we're all right. I'm going to put everybody back on the screen. Actually, no, wait a second. Dave, you're on my screen right now. What are you working on? Where can people find out more?
I am currently freelancing Universe Today and Sky and Telescope. I do mostly the visual, what to see in the night sky beat for Universe Today, and I do the space flight beat mostly for Sky and Telescope. So I am covering, of course, the Hayabusa return and Chang'e return and all the other like space flight missions that are going on. And I'm doing a roundup on what's going on for 2021 for both for space flight and observational astronomy. That'll probably be by the end of this month. That's the usual big post of eclipses, occultations, conjunctions, solar activity, everything that you can imagine. So, and old book is out, and this one is still, it's got all the stuff going on till 2024. So all the observational astronomy stuff is still valid. And new book, Christmas is coming up. So they're on Amazon. They're out there for sale.
Right on. I highly recommend them. Moya.
Hello. You can find me on Twitter at GoAstroMo. I am getting ready for my last semester of a PhD program. Very excited about that. And I host a podcast called ExoLore. It's all about fictional world building. So I imagine other worlds, but with facts and science. You might get a kick out of it.
I give that a listen to occasionally. It's a good podcast.
Oh, thanks, Dave.
Yeah.
Brian.
You can find me on Twitter at Brian Coberline. You can find me at University Today, where I'm writing articles. And you can find me on my website, which is briancoberline.com. Having an unusual name makes me easy to find.
I know the feeling, except for being very similar to a person on a television show. All right, so I have an interview coming up tomorrow with a scientist. Oh, I forget how to pronounce his name. I apologize. That's tomorrow morning about resource harvesting and manufacturing on the moon. So if you're interested in both acquiring regolith and turning it into things, you're going to want to catch this interview tomorrow. New writers joining us on Universe Today, I'm quite excited about. David Portree is a space historian, and he's working on some articles for Universe Today as well, and maybe some other.
I saw Alan Boyle's back.
And Alan Boyle has
He's
rejoined us back on Universe Today as well. And Alan, of course, is like one of my mentors in the space journalism field. Was working long before I began, and was willing to give a fresh young space journalist some tips and hints, and I'm just super excited that he's mostly retired, but I'm able to give him an outlet on Universe Today to keep writing. So our coverage on Universe Today has just been getting better and better. I'm so excited about how comprehensive and how quickly the news is getting out, and just how many great people are working on the team. So I know some of them are here right now, but just to everybody on the team, thank you for all of the work that you're doing. I know that, I feel like we're doing a good job of communicating the space news at the same time that we're entertaining people. And so it's great. It's been a good year, actually, for Universe Today anyway. All right, I can put everybody back on the screen. There they all are. There's me back at my window. Thank you, everybody, for joining us today for the Weekly Space Hangout. This is a big week. Thank you to all of the moderators for handling the comments. Thank you, of course, to Nancy Graziano for herding all the cats and keeping us all organized. We couldn't do this without you. We will see all of you next week. Thanks, everybody. Stay safe.
Bye.